Okay, we've talked about Newton's third law a few times. We haven't done any like real calculations with it, except for the questions we did with one block being attached to another block and then like pulling it along, like the question we did with the with the horses pulling the two logs. Okay, we did that question. That's actually a Newton's third law question. Okay, so any questions where we had one thing attached to another thing, but we were only applying a force on the first one, but they were both going along, kind of system questions, those are actually a type of Newton's third law question. Okay, here's the good news. Even though we say this is a Newton's third law question, there is no new math for Newton's third law. When we're solving a Newton's third law question, we use Newton's second law to do it. Okay, because the rules all still apply. Okay, force is still mass times acceleration. Okay, it's still F net is still the vector sum of all forces. That doesn't change. Okay, what Newton's third law deals with are action-reaction pairs. Okay, Newton's third law is the most often quoted and most often misapplied of his laws. Every action has an equal and opposite reaction. Okay? Most of the time this is somehow misapplied to like sociological situations in which it does not apply. Like you say something awful to somebody and they smack you on the mouth for it. Okay? And they're like, oh, every action is an equal opposite. No, you said something awful and you got smacked for it. Not that I condone physical violence, because I don't, but okay, those are the kind of situations it gets misapplied to. It does not apply there. Okay? It applies to everything else in terms of movement. Okay? Like for example, if I push on this wall, what does the wall do? Pushes back on me. Hard, because I pushed on it really hard. Okay? Did the wall accelerate? You guys didn't hear it flex? I heard flex. See? Flex. It accelerated. Okay? And so did I. All right? I went the other way. I pushed on the wall. I went the other way. My mass is less than the wall. Okay? So the wall experiences a lot less acceleration than I do. What we both experience the same is the what? My acceleration's different because my mass is different. But what's the same for both of us? The force. Okay? This is why people don't always get Newton's second law, because they look at a situation in which it applies and it doesn't look equal. Okay? So, smart car versus semi-truck. Okay? They run into each other. Forces are equal. But what we see doesn't look that way. Okay? We see one thing getting, pushed by the other considerably. Okay? It looks like the smart car fares a lot worse off, but it's actually the same force. But because the masses are so different, the accelerations are different. Okay? It doesn't matter how different the two masses interacting are, the forces are equal. Okay? That's the hard thing to get around visually when we see those kinds of situations. Okay? So we use Newton's third law for all kinds of things. Okay? But what we have to understand is Newton's third law says that all forces act in pairs. Every action has an equal and opposite reaction. That's an action-reaction pair. The wall and me, that was an action-reaction pair. Okay? Understand what is meant by normal force. We've been using normal force all along. Normal force is the reactive force. Okay? It's that force that comes back. Okay? And obviously for every action, there's an equal and opposite reaction. Okay? So, if we see like football players lined up across from each other, okay, and the ball is snapped, they crash into each other, all right? Are the forces equal? They absolutely are. Okay? But if one line is heavier than the other, okay, they may accelerate that line forward or backward. Okay? If you're the defense, you want to push forwards. If you're the offense, you do not want to get pushed backwards, because then they might sack your quarterback. Okay? So that's why linemen are usually the bigger guys on the team. Okay? They're harder to push around, just like sumo wrestlers. Okay? The bigger they are, the harder they are to move around. Okay? The less their acceleration will be because of their larger mass. Okay, and if you've ever blown up a balloon and let it go, okay, that's also Newton's third law. Okay, so if you blow it up, okay, you've got air pressure pushing on the inside of the balloon, and because the balloon is made of rubber and it's elastic, it pushes back on the air. If you let it go, okay, that reactive force forces the air back out of the balloon and it flies all over the place. Okay, everybody with me on that? The same is true for rockets. Okay, this is how rockets work. Right? They exert a certain amount of force, okay, because of the gases that are being released at a high rate of speed out the engines. Okay, so we've got all this pressure building up and it's released through the engines, okay, and they push on the spacecraft. All right? Where is the acceleration of the spacecraft the greatest? When it first leaves the launch pad, or when it's just about to, let's say, eject the thruster engines? Just when it's about to eject the thruster engines. What does it have a lot less of at that point? Because it's used up all of its fuel. The acceleration gets greater and greater and greater on a rocket as it goes, because its mass is constantly decreasing. Okay, it's using up all that fuel. The heaviest part of launching a rocket is all the fuel. Okay, that's why they blow up so often. Okay, they're just a big explosion waiting to happen. Okay, well, they're a controlled explosion, hopefully. Okay, and so we're just releasing all of that energy from the stored fuel. But as we consume the fuel, it gets lighter and lighter and lighter. All right, everybody okay with that? Okay. All right. So you got in your boat, and too late, you realize you don't have the paddles. So here you are. Can you run along your boat and jump onto the dock? Okay, it would help. Doesn't have to be, but it would help. You're right. If the boat was heavier than you, that would definitely help. Like, yeah, if this wasn't a canoe and it was a big container ship, right? Everyone would be like, yeah, I can totally jump off there. I'd probably die on a fall, but okay, I could totally jump because yeah, it's so heavy. I wouldn't move it at all. Okay, but we picture this canoe, and we picture ourselves running through it, and we picture the canoe sliding underneath us. Yeah, it's going to do that. But if you exert a force on it, what does it have to do? It has to push back. Newton's third law says it has to. So whatever force you exert on the boat, it's got to exert a force on you in the other direction. Okay? Now, I'm not saying this would be easy and you would require great balance and timing and all of that. Otherwise, the dock is going to be full of your chicklets. Okay? But we could certainly do it. Yeah. Okay? The key here is kind of direction of force. If you push straight backwards, your chances are less. Because yeah, as you run along the boat is going to move along underneath you, okay? It's going to move underneath you, but you should still be moving or staying at least in one place or moving slightly forwards, okay? But what if instead of directing the force this way, I direct it like this? Would that help? If I direct my force at an angle, now I'm not just pushing on the boat, I'm pushing on all the water underneath it. Okay? Does that make the mass I'm pushing against a lot bigger? So its acceleration would be a lot less. Agreed? Okay? And there's less of that, the boat's moving backwards part of it. Okay? It's about direction of force. But even if I just ran along that boat, that theoretically, technically, it's possible to jump to the dock. Okay? The boat has to push back on you when you push off on it. Okay? Everybody with me there? It's strange, but it's true. Okay, so let's imagine this. You're out in space, okay? And you're doing some repairs on the spacecraft, okay? And you push on the spacecraft, right? Is that going to be a similar situation to me in the wall? Right? Like when I push on the wall, I move away from the wall. The wall moves away from me a little, okay? The same situation here. Does the spacecraft move? Hands up if you think the spacecraft moves. Absolutely it does, okay? Not a lot, okay? And for how long? How long is the acceleration of both me and the spacecraft going to last? Right. As soon as I lose contact with it, now we both move at a constant velocity. Okay? For the spacecraft, that's going to be small. For me, it's going to be a lot bigger because I accelerated a lot more because of my much smaller mass. Now, could that cause a problem if nobody corrects for it on the spacecraft? Like, let's say this thing was put on a course for Pluto. Okay? I do this in Earth orbit. Is it going to get to Pluto? It would get that far, but it wouldn't be at Pluto because I gave it a little nudge very early on. Okay? And so instead of following this path that ends at Pluto, okay, over the course of like 7 years or however long it would take to get there, okay, now it ends up over there. Okay? These are the things that someone in like astrometrics, okay, has to think about. They have to account for every little force. That's why we give so much credit to rocket scientists. Okay? There's a lot that they have to account for. Every little thing that can push or pull on that spacecraft has to be accounted for. It's why they don't just launch a spacecraft, point it at wherever it's supposed to go, and leave it alone for 12 years. Okay? They have to make course corrections all the way along because little things, it passes an asteroid or it passes another planet and does a slingshot around it. We got to account for all those things. Okay? So those are all kind of Newton's third law kind of calculations that have to go on. In fact, the whole gravity slingshot idea is a Newton's third law idea. Okay? You actually steal a little bit of momentum from the planet that you slingshot around. Okay? Now, if we're talking about slingshotting a small spacecraft off of Jupiter, Jupiter doesn't mind giving us a little tiny bit of momentum because it doesn't really affect Jupiter at all. Okay? But it can make a big difference to getting a spacecraft where it's going in 10 years versus 15 years. Okay? But it's still a force was exerted. Okay? All right, now, here's where you want to be glad you're in my class and kind of not in Mr. Dickey's class, because he starts talking about like the attraction between things, and he makes people tell them that they're attracted to each other when it's true, because it's gravitation, but it's awkward. It makes people feel really awkward, okay? But it's a Newton's third law thing, right? You've got one force pulling, another force has to pull back. Okay. All right, so let's look at this situation here. Okay, we got a mass of 11,000 kilograms. That's the spacecraft. Okay, we have a mass of the astronaut, 92 kilograms. It's a heavy suit. Okay, so the astronaut exerts a force of positive 32 newtons, or 36 newtons, sorry, on the spacecraft. Can I calculate the acceleration of the spacecraft? Okay, so acceleration would be F net, that's going to be the only force because we're out in space, divided by mass. 36 newtons, positive 36 newtons, divided by 11,000 kilograms. We're not talking very much force here. Okay, I think I have it on the next page here. Or the next page. Okay, so for the spacecraft, 0.0033 meters per second squared. All right, that's a tiny acceleration, but it does impart a small amount of velocity to the spacecraft that would have to be accounted for. Okay, we do the same thing with the astronaut, but in the opposite direction. The force on the spacecraft was positive. The force it exerts back on me as the astronaut, okay, is going to be negative. My acceleration is considerably larger, still not very big, but it's considerably larger than the one experienced by the spacecraft because of my smaller mass. Okay. Everybody all right with that? Okay. So this kind of relates to the friction stuff we were talking about last week, right? Like why picking up the desk and pulling it towards me is so much easier than if I push down on the desk and try and push it forwards. Okay? Because when I push down, what does the floor have to do? What's the floor have to do when I push the desk into it? Push back. It has to push back. Okay? The harder I push, the harder the floor has to push back. Okay? That's going to increase the normal force to push back, and it's going to make the friction greater because friction is normal force times the coefficient of friction. Okay? So Newton's third law plays a big part in our friction calculations. Normal force is that reactive force from Newton's third law. Okay? Everybody all right with that? Okay. If you want to jump, what do you have to do? Besides like bend your knees and all that kind of stuff. In terms of forces. Which way do you push? You push down. Is that counterintuitive? You jump up. How does pushing down make you jump up? If you bend your knees and exert lots of force onto the floor, more than your own weight, the floor has to push back. So if you exert a force on the floor greater than your own weight, the floor pushes you up with a force greater than your own weight, and you accelerate upwards for as long as you can exert that force. Okay? The stronger you are, okay, the higher you can jump. Okay? But it's weird. It's weird but true. To jump, you actually push on the floor. You push downwards, and the floor throws you up in the air in response. Okay? Strange but true. Okay, now if I push on the floor, when I jump, what happens to the earth? Right? I accelerate upwards. What does the earth do? Does the earth accelerate downwards? Newton's third law says it has to. Right? Newton's third law says every action is an equal and opposite reaction. If I push on the floor with 1,500 newtons worth of force, I'm going to accelerate upwards because the earth is going to push on me with 1,500 newtons worth of force. So technically, the earth should accelerate downwards when I push on it. And it does. Do we have to worry about that? If everybody jumped at the same time, could we knock Earth out of orbit? Some people think so, but we can't. Because this is the mass of the Earth. .98 times 10 to the 24 kilograms. You are going to have virtually no effect on that kind of mass due to your jumping. Even if the entire population of the Earth were to jump in the same place at the same time, the amount of energy imparted to the Earth is negligible from that force. Okay? There'd be a lot of logistical problems with having everybody in the same place at the same time. That would be a big crowd. I don't like crowds. That'd be a big crowd. Okay? Just think of the sanitation problems. There was actually a person who did like this theoretical study on what the effect of the whole world population being in the same place at the same time and jumping on the Earth. And what he discovered was it would end human civilization. Because everybody in the same place at one time would require far more resources than any place on Earth could possibly ever give. Okay? Now you're trying to imagine getting everybody out of there. It's crazy. But it would have no effect on the Earth. It would just keep on going, okay, without us do that. Okay, so Nike took this idea and said, people are generally stupid. So we're going to make this ad, and people bought it, okay, about making the Earth spin by running. Okay, I'm going to show you this video because okay, there's zero chance you could ever get the Earth moving or rotating if it had stopped. And also, if it stopped, there's a lot of atmospheric problems that would go on because the Earth's atmosphere would keep moving. Yeah. Plus, there's all that like convection and stuff, and one side of the Earth would roast and the other would freeze, and that won't work. So yeah, but the idea, I mean, you know, Newton's third law. If you push on the Earth, it's got to push back. But we're talking about way too much mass to possibly move. Okay, now here's a way that we can use, or that Newton's third law is actually used. Okay, how many people have ever seen like somebody with like a little tiny Honda Civic pulling like a U-Haul moving trailer behind it? Okay, like people have these really small cars and they're pulling these U-Haul trailers behind them. Small cars generally don't have brake connectors for trailers, okay? So generally, if you want to tow a trailer safely, you have to plug the trailer into your car where it has a brake controller. And that supplies electrical power to the brakes on the trailer, which makes it way safer. It will never jackknife, okay? Which is Newton's first law. You stop, trailer keeps going, okay? You don't want that to happen. So what U-Haul devised is a reaction control braking system. So in the hitch, okay, where the hitch goes over the ball, okay, there's actually a spring-loaded mechanism behind the ball. And so if you start to brake, the trailer, according to Newton's first law, continues to move forwards. And that spring-loaded brake mechanism pushes against the ball. And the ball pushes back, actuating the brakes on the trailer. So it actually uses Newton's third law to apply the brakes without using any electrical hookup. So a car, like a Honda Civic, something like that, okay, something really small that doesn't have a brake connector, can still somewhat apply the brakes on the trailer. It's also why they have like 20 stickers on the outside of those trailers saying maximum speed 80 kilometers per hour. Okay, because it's not safe to try and use that mechanism faster than 80 kilometers per hour. If you slam on the brakes, the trailer is just going to keep going, and it's going to pivot around that hitch ball and come right around and smack the side of your car. Okay, obviously we don't want that happening, so that's why you cannot or should not drive one faster than that if you don't have electronically controlled brakes. But this is a Newton's third law reaction control braking system. Okay, everybody all right with that idea? Just practical application of it. Okay, well, let's look at a couple of examples here. I'd like you guys to write this example down, draw the picture. Yeah, I'll give you a couple minutes and then we're going to walk through how to solve this one together. Okay, so we've got 3 boxes here. Is this a system? Right, look, we got 3 separate masses here, and it says the acceleration of the boxes is 1.5 meters per second squared. They're all accelerating together, so this is a system. Are there individual forces acting on the individual parts of the system? Right, like, I mean, we could easily just draw this and say, okay, there's 23 kilograms worth of mass, and there's this applied force, and it's all accelerating. Yeah, we could say that. Okay, it says it's frictionless, so that would be the situation. But here's the thing. I'm not told that applied force. And they want one of the forces that's inside of the system. They want the force exerted by box C on box B. Okay, so here's the chain of events that goes on in this. It's going to kind of sound like that story about the lady that swallowed the spider to catch the fly, and it kind of goes along like that. This box pushes on this box, and it pushes back, and then this box pushes. And, okay, so we start out with this force pushing on box A. Okay, when the force pushes on box A pushes on box B. What does box B do? It pushes on box C, but it also pushes on box A. That's the reactive force. So there's a whole bunch of action-reaction pairs. So yeah, it definitely pushes on box C. Okay, and actually that's really important for this question. So what I have to do here is actually split this up so that I can look at the forces acting on all 3 boxes and see if there's a way for me to get to this force. Okay, so box A. Okay, box A is 8 kilograms. Okay, there's an applied force from the hand, and then there's this force. That would be the force of B on A. Okay, force of C on B is definitely not part of the equation for that box. Would you agree? All right, I can't use this box. This box is not going to help me get the force I'm looking for. Okay, box B, okay, is 10 kilograms. This is the force of A on B. Okay, that's the force of A pushing B forwards. What would this force be? This is the force of C pushing back on B. Remember, there's no friction here. Okay? The force that's acting back on B has to be from C pushing back on it. This is actually the force they want me to find. Here's my problem. I don't have any way to find that because I don't know this force. I could get the net force. That's no problem. The net force on box B is 10 times 1.5. All right, yay, it's 15 newtons. That doesn't help me. I don't know either of the two forces that contribute to that. This is usually where people quit. They're like, okay, well, that's the force I'm supposed to find. I got no way to find it. I quit. Okay, is there still a third box? Okay. So the third box is box C. It's 5 kilograms. How many forces are acting on box C? Besides, let's not include gravity and normal force. We'll ignore those for now. 1. The only force acting on box C is B. So B pushes on C, and C pushes back on B. Is that an action-reaction pair? Right? According to Newton's third law, every action has an equal and opposite reaction. So when B pushes on C, C pushes back with an equal but opposite force. So these two forces are equal in magnitude but opposite in direction. Everybody okay with my logic there? Okay, so if that's the only force acting on C, is it also the net force? Should be. Do I know the mass and the acceleration of box C? Right, here's the acceleration. All the boxes accelerate at that rate. Okay, so 5 kilograms times 1.5 meters per second should be 7.5 newtons. Okay, so the force that B exerts on C is 7.5 newtons forwards. What's the force exerted on B by C? Every action has an equal and opposite reaction. B pushes on C with 7.5 newtons forward. C pushes on B with negative 7.5 newtons, or 7.5 newtons backwards. Okay. How much calculating did we actually have to do in that question? Like, I calculated this here, but I didn't need to. I did one calculation to answer that question. Did I do a hell of a lot of figuring before that? Okay, and was it really convoluted reasoning? That's what's tricky about Newton's third law. The math of Newton's third law is even easier than the math we were doing for Newton's second law questions. Okay, what's tricky is, okay, so she swallowed the spider to catch the fly, and then she did, I can't remember how it goes after that. Swallowed a frog to catch the spider. No, it's something weird like that. Okay, you have to keep going along and going, okay, that box isn't going to help me. None of the forces there are equal to the force I'm looking for. Oh, here's the force I'm looking for, but I can't use this box to get it. Somewhere in this system, is there an action-reaction pair for that force? If there is, it's equal in magnitude, but opposite in direction. So I go to the last box and I go, yes, there's the force that's equal to that force, but in the opposite direction. This is the one that causes that one to happen. Action, reaction. Okay? There's a bit of convoluted reasoning that goes on in a Newton's third law kind of question. Okay? All right, everybody follow what we did there? This is where you really have to be able to break down a force system, figure out what's really going on inside. Okay, so same situation. Okay, so we still know that the acceleration in here is 1.5 meters per second squared, and we know the force of C on B is 7.5 newtons backwards, and we know the force of B on C is 7.5 newtons forwards. Okay, so now, using that, calculate the force that B exerts on A. The first thing you'll have to do is figure out which box you're going to have to use to do this. It may not be the one you think. Give you a few minutes on that one. Okay, so I can't use A because I don't know the applied force on A. That's not going to work. Okay, but here's what I know about box B. I know its mass, I know its acceleration, so I know its net force is positive 15 newtons, 1.5 times 10. Okay, this is the force A exerts on B. It's the force that's pushing B forward. But if A pushes on B that hard, B has to push back the force I'm looking for on A with a force equal to that, but in the opposite direction. Okay, here's the other force we know. The force of C on B. We calculated that in the last question. So we know this force here is 7.5 newtons. Okay, because we calculated it in the last question. So if I know this plus this equals 15, can I calculate the force A exerts on B? I sure can. This is just a Newton's second law question. Now that I've figured that Newton's third law part out, now F net equals the force of A on B plus the force of C on B. All right, all I have to do is bring the force of C on B over, so I'll have positive 15 newtons minus negative 7.5 newtons equals the force that A exerts on B. So that's going to be 22.5 newtons forwards. So if A pushes on B with 22.5 newtons in a forward direction, B pushes on A with negative 22.5 newtons. We only have two significant digits there, so it would end up being 23. Okay? Everybody all right with my logic there? But it takes a while to get to it, doesn't it? But in the end, I didn't have to do much math. Okay? I had to figure out net force, 10 times 1.5, and then I had to subtract negative 7.5 from 15. Okay? Two pretty simple calculations, but getting there is the challenge. That's always the challenge with Newton's third law questions. Okay? All right. Okay, so similar idea. Only two boxes this time. But now there's friction. Doesn't change a thing. Still a Newton's second law problem at its heart once you figure out who's reacting with who. Okay, once you've got that, okay, same as always. Draw your boxes separately, figure out what forces are involved, and see if there's a way to get to what you're looking for, which is the force exerted by B on A. Okay, so write it out, guys, whole question diagram. Okay, get started on that. Okay, so we didn't do the two log question, did we? I think we did. Okay, write this one down, give it a try. Okay, it's very similar to what we've been doing. Okay, don't let the fact that it's chains connecting logs make you feel like it's any different than two boxes pushing on each other. It's not the same idea. Okay. Okay guys, so if we're just drawing this out, okay, we got the two logs, okay, they're connected by that chain, and then there's 2,600 newtons worth of force, okay, connected to the first log, okay, so the first log is 150 kilograms, and the second one is 250, okay, and then the total friction on the whole system is 2,400 newtons. So the first part of the question is really a Newton's second law question, right? You got 400 kilograms worth of mass being pulled this way by 2,600 newtons and resisted by 2,400 newtons. Okay, is it pretty straightforward to get the acceleration of the system? Okay, so our net force is 200 newtons. Okay, so our acceleration is 200 newtons divided by 400. All right, so that part's easy. Okay, our acceleration is 0.5 meters per second squared. Now you have to break it up, box by box. Okay, there's a way to do it for each box. Okay, or sorry, for each log. Okay, you could use the 250 or you can use the 150. They'll both arrive at the same answer. It's just different points of view. Okay, you do have to do one extra calculation if you're going to use the 250. Okay, so give you a few more minutes on that one here, guys, before we start it. But just know that at this point you've got to pick a log and isolate it. Okay, identify the forces acting on it. Okay, there's an action-reaction pair in there for that force. So you can either calculate that force directly or calculate its action-reaction pair and know that it's equal and opposite. Both ways to do it. Okay. All right.
Good morning,
We'll start
everyone.
tomorrow with that one. You can try it at home tonight if you want.